Hello, my name is Ayman Al-Hajjar. Welcome to the lecture on Security and Safety Fundamentals, which is part of the Safety Informed Security Lecture Series for SciBook. This lecture introduces the core distinction between security and safety, and then explains why that distinction becomes much less clear in connected and cyber-physical systems. The purpose of this lecture is not to replace either discipline with the other. Security and safety have their own histories, methods, assumptions, and standards. The point is that modern systems increasingly force us to reason about both together. A useful way to think about this lecture is through a simple question. What happens when a security breach changes the behavior of a system that can affect people, physical processes, healthcare infrastructure, or the environment? In that situation, a security issue is no longer just about data, access control, or network compromise. It became a safety issue as well. By the end of this lecture, you should understand what we mean by security, what we mean by safety, why they were traditionally treated separately, and why security-informed safety is now needed for connected systems. The lecture maps primarily to introductory cyber concepts and cyber-physical system security, but it also connects partly to risk management and governance because safety and security both depend on structured risk reasoning, and of course to adversarial behaviors because intentional attackers are central to the security side of the problem. The important point here is that security-informed safety sits across several knowledge areas. It's not only a network security issue, it's not only a safety engineering issue, it requires concepts from security, risk, adversarial behavior, infrastructure, and cyber-physical systems. So what we're going to do, we organize this lecture into 5 main sections. First, we define security, then we define safety. Third, we look at the traditional separation between the two, the historical separation. Fourth, we explain the convergence problem, where connected systems make that separation harder to maintain. And finally, we introduce security-informed safety as a way of reasoning about both concerns together. Let's start first by looking at what is security. Security protects information systems, data, and services from unauthorized access, harm, or misuse. The important terms here are information systems, data, and services because security is normally concerned with protecting digital or information-based assets. This, of course, includes unauthorized access, preventing misuse, preventing disruption, and preventing the behavior that the system is expected to provide. In most cybersecurity teaching, security is commonly introduced through confidentiality, integrity, and availability. Confidentiality means information is not disclosed to unauthorized parties. Integrity means data and systems are not tampered with or modified in unauthorized ways. And availability means systems and services remain accessible and functional when they are needed. For traditional IT systems, this framing worked very well. For example, if an attacker steals customer data from a database, we can describe this as confidentiality breach. If the attacker modifies the data, we can simply describe it as an integrity breach. And finally, if the attacker disrupts access to the system, we can describe this as an availability breach. However, in connected systems, security failure can also affect physical or operational behavior. That is where the lecture starts to move beyond standard information security. To understand security properly, we need to break it down into assets, threats, and vulnerabilities. So let's look at it from this concept. So we spoke about the security principles, confidentiality and integrity and availability, where we said confidentiality is not disclosed, information is not disclosed to an authorized party, integrity, data and systems are not tampered with or modified, and finally availability, systems and services remain accessible and functional. Now, what are we actually trying to protect? Security protects data, systems, infrastructures, networks, and communication. And the threat source includes attackers, adversaries, unauthorized users, software vulnerabilities, exploits, misconfigurations, and so on. And that is useful because security is not just about the attacker. Security incident usually requires several things to align together. There need to be something valuable to protect, a weakness that can be exploited, and a threat source capable of exploiting it. In practical security work, this is why we spend time identifying assets, modeling threats, finding vulnerabilities, and selecting controls. Now you can see here how we can visualize that relationship between asset, threats, and vulnerabilities. So this slide shows the three core ideas of the asset, threats, and vulnerabilities. And assets are the things that we care about. They might be data, systems, networks, services, credentials, or operational capabilities. Threats, of course, are the things that may cause harm. In cybersecurity, threats often include attackers, malware, hostile insiders, botnets, exploit kits, or even organized groups. And finally, vulnerabilities, which are the weaknesses that make compromise possible, make the threat more dangerous. They may include bugs, weak configuration, exposed services, default credentials, poor access control, or even insecure design. And the security problem is that threats exploit vulnerabilities specifically to compromise assets. That's the ultimate goal for malicious attackers. That is a simple model because it's powerful, and it explains why cybersecurity controls can intervene in different places. We can harden the asset. We can reduce the vulnerabilities. We can detect threat. We can, of course, limit the access, monitor behavior, or reduce the impact of compromise. Let's have a look at this practical example, a simple example. We have an example here where we can consider a database with weak credential. An attacker accesses it and steals customers' data. The vulnerability is the weak or default credential. The threat, of course, is the attacker scanning for exposed systems and trying common passwords. And the compromise is unauthorized access to the customer records. The impact, what matters for us, which is it can include data breach, regulatory penalties, financial loss, and reputational damage. That's what matters for us as business. That's what matters for business users because this is where the assets are compromised. The breach path matters. If we remove the vulnerability, reduce the threat opportunity, or protect the asset, the path changes. For example, strong authentication, network segmentation, access monitoring, secure configuration, all of those would make this attack harder. The important part is that security reasoning often traces how a threat reaches an asset through a vulnerability. Now, this is one side of the story. Now let's move to define safety, and this is what the safety informed is. So, what is safety? Safety is a state of being protected from danger, injury, or loss. In engineering, it means that systems operate without causing harm to people, the environment, or critical operations. That is a different starting point from security. Safety is not primarily about unauthorized access or malicious activity. It's about preventing harm, more often physical harm. In safety engineering, we often think in terms of hazards, risks, and controls. A hazard is a potential source of harm. Risk combines likelihood and severity, and controls are the measures used to reduce the likelihood of harm, reduce its severity, detect dangerous conditions, or recover safely. Safety is therefore closely connected to assurance. It's not enough to hope that the system is safe. We need structured reasoning, evidence, testing, analysis, and review to build confidence that the system behaves safely under expected and abnormal conditions. So let's look at what safety protects and what it protects against. So if you want to define the safety principles first, safety protects human health and life, environmental integrity, and critical infrastructure function. It protects against equipment failures, environmental, conditions, human errors, and increasingly malicious interference. And the last point is important because traditional safety engineering has always considered faults, failures, misuses, and abnormal operation conditions. But malicious interference changes the assumptions. An attacker now is deliberately trying to cause the system to enter an unsafe state. They may also, of course, try to hide that unsafe state from operator. So the safety principles in this sense are the hazard control, risk management, and the assurance. The safety protects human health, life, environmental integrity, and critical infrastructure functions. Now, let us now look at hazard, risk, and control as a safety side equivalent of asset, threats, and vulnerability, similarly to what we did there. So, we have the relation between the hazard, risk, and control, where the hazard is a source of potential harm, Risk is the combination of how likely the harm is and how severe the harm would be. And finally, control is a measure that reduces or manages the risk. For example, think about a medical ventilator failures. What can create? It can create a patient safety hazard. The risk depends on the likelihood of failure and for the possible severity of potential of patient harm or possible patient harm. Controls may include alarms, backup power, maintenance check, clinical escalations, procedures, and so on. The safety problem is that hazards create risks that must be managed and controlled. This mirrors the security model, but it's not identical. If you think about it, in security, we're often asking how an attacker can compromise an asset. In safety, we are often asking how a system can create harm and what or how that harm can be prevented, detected, or mitigated. So far, security and safety looks related but kind of distinct. The next question is why they were traditionally treated as separate domains. So security and safety have traditionally been treated as a separate domain because they developed in different contexts. So security grew strongly in IT, networks, software, military system, information protection, access control, and so on. Safety, on the other hand, grew strongly in industrial systems, mechanical systems, transport, healthcare, aviation, process control, and so on. Security typically assumes intentional adversaries. Safety traditionally assumes accidental failures, environmental conditions, equipment faults, and human error. These assumptions led to different methods, different professional communities, and different regulatory framework. Let's try to look more at that traditional separation. So the traditional separation made some sense historically. It was different context. Safety emerged in industrial and mechanical system, where the central question was how to prevent accident and harm, while on the other hand, security emerged in IT and military domains, where the question was how to prevent unauthorized access, misuse, and compromise. The threat model were also different. Safety focused on accidental failure, while security focused on intentional adversaries. The engineering approach was also different. Safety relied on redundancy, fail-safe design, hazard analysis, and assurance, while security and data protection regulations focused on privacy, access, governance, resilience, and so on. So let's try to compare them side by side. So you have here the primary concern for security and for safety, which are in terms of threat model, focus, risk approach, typical domains, and regulatory view. So security is concerned with malicious attackers, systems, data, services, vulnerability-based reasoning, and IT or network systems. Safety, on the other hand, is concerned with failures, as we said, and accidents, people and the environment, hazard-based reasoning, and safety-critical systems. This separation is not really wrong. It just reflects real differences in the two disciplines. The problem is that modern connected systems increasingly combine both types of concern. So why this separation no longer works? So the separation becomes difficult when a security breach can create a physical safety consequence. Consider, for example, a hospital insulin infusion pump. If an attacker compromises the pump and instructs it to deliver an unsafe dose, the event is both a security breach and a safety failure. It's a security breach because obviously unauthorized access has changed the device behavior, but it's also a safety failure because the changed behavior can cause patient harm. In this situation, analyzing only the security side is incomplete, and similarly, analyzing only the safety side is also incomplete. We need to understand how the security breach creates the safety consequence. So let's look at the convergence problem, where the connected system blur the boundary between security and safety. So connected systems in general, for example, industrial systems, are now networked through IoT and cloud services. Medical devices communicate wirelessly. Autonomous vehicles rely on connected sensors. Smart buildings use distributed sensors, automated controllers. Logistics use GPS, telemetry, and dashboards to make operational decisions. When these systems are compromised, security breaches can create safety failures. A compromised sensor will lead to incorrect control decisions. A malware in medical devices will lead to treatment errors, or may possibly lead to treatment errors. An attack on power grid may lead to cascading failures. False data may be worse than missing data because operators may trust that this data are correct and make the wrong decisions. And the core issue is that malicious attackers are now a safety threat. Traditional safety assumes accidental failures. Connected systems require us to consider deliberate attacks as part of the safety reasoning. Let's look at some examples. We have some real-world examples of security safety convergence. We have a medical device and wearable which are clear examples. Pacemaker, insulin pumps, glucose sensors, and heart monitors increasingly depend on wireless communication, software, data integrity, and reliable monitoring. A security flaw, for example, remote reprogramming, data interception, or even device spoofing, can lead to false reading or incorrect medical decisions, which is, of course, can lead to patient at risk. Autonomous vehicles provide another example. They rely on GPS, sensors, and vehicle-to-everything communication. GPS spoofing or sensor manipulation can affect how the vehicle perceives the environment. The safety impact may be collision, or unsafe steering, or failure to respond to hazards. A third example is an industrial control system and SCADA environment, which are also important. Weak authentication, unencrypted protocols, or exposed control interfaces will allow basically attackers to interfere with critical infrastructure. The safety impact may include blackouts, industrial accidents, or again, cascading operational failure of several different industries and several different services in one go. And these examples motivate how we're going to look at security and informed safety. So the principle is simple. If it's not secure, it's not safe. Security-informed systems mean integrating security thinking into traditional safety engineering. The core idea is that a system cannot be treated as safe if security failures can cause it to behave unsafely. Security breaches become a new class of hazards that safety engineers must address. This does not mean that security replaces safety. It means safety analysis must include security-relevant causes of unsafe behavior. And the practical implication is that safety engineer must understand cybersecurity threats. They need to understand cybersecurity threats. Security engineers need to understand safety implications of breaches, and teams need to work together. Both the safety and the security teams need to work together on risk assessment, mitigation, testing, and assurance. And this brings us to the new security-informed safety view, the integrated view. The primary concern is not just protecting assets or preventing harm separately. It's protecting assets, people, services, and physical systems together. The threat becomes both accidental failure and intentional attacks. The focus includes now systems, data, services, and human safety. The risk approach combines vulnerability analysis and also hazard analysis, and the typical domain is connected and cyber physical systems. Security-informed safety considers how security failures can change system behaviors and create safety-relevant consequences. So let's look at some examples of real security safety convergence incidents. Stuxnet is often used as a classic example of security safety convergence. It targeted Iran's Natanz nuclear enrichment facility, and it compromised PLCs. It manipulated centrifuge speeds and reported normal operation while causing damage. The cyber attack affected the physical equipment. Another example, which is more recent, is the Ukraine power grid attacks. Attackers gained remote access to SCADA systems in power distribution. And in 2015, malicious commands were issued manually. In 2016, Destroyer malware automated part of the attack, and the impact obviously was quite severe, a blackout affecting large number of people. These examples show why security and safety cannot always be analyzed separately. When digital compromise affects physical operation, cybersecurity becomes part of safety reasoning. So what we covered today? The lecture today introduced the foundation for the rest of the model. Security is about protecting assets from unauthorized access, harm, or misuse. Safety, on the other hand, is about protecting people, the environment, and critical operation from harm caused by system failures. The traditional separation made sense when systems were isolated and the assumptions were different. Security focused on malicious adversaries, safety focused on accidental failures and hazards. Connected systems blur this boundary. Security breach can now become safety hazards, especially in cyber physical systems, medical devices, industrial systems, autonomous vehicles, and critical infrastructure. Neither discipline is sufficient alone. Security without safety may ignore physical impact. Safety without security may ignore intentional threats. Security-informed safety brings the two together. It asks how the system failure can create unsafe behavior and how system can be engineered, analyzed, and assured with both concerns in mind. This is the foundation that we looked at today that will prepare us for the second lecture in the series, where we move deeper into security-informed safety as a concept and start to examine how it changes engineering practice. These are some of the key references that I would recommend if you want to read more about things that we covered today, that you can go through those. Thank you.